Whenever you're ready.
Okay, so this is going to be the 8th talk in our series, the last for this year, but we're really excited to host Angela Shoellig from the University of Toronto. She's an associate professor. She's got like a very large list of awards and honors on her resume, so I'll just read out a few that I can manage. So she's like a Canada Research Chair, and yeah, she's I guess the RSS Early Career Award, and she was also featured in the MIT Tech Review's 35 under 35 a couple of years ago. But yeah, I know her from a lot of her work, particularly in robotics, control, and more recently learning. Incidentally, we've had the first speaker in this series from U of T, Florian Chakrathi, did the opening talk, and it's nice to have, again, people from U of T to do closing. Over to you, Angela.
Great, welcome everybody. It's a pleasure to be part of the Mila seminar series. And I really hope we can strengthen the connection between Toronto and Montreal and and leverage each other's strength. So I'm an associate professor at the Institute for Aerospace Studies at the University of Toronto. I'm also a faculty member of the Vector Institute. And today I'm going to talk about how we combine models and data for improved performance and safety in robotics. So we envision a future where robots navigate on our roads and in our skies, where they support us in our daily tasks, such as, in the kitchen or, handicapped people, supporting them to walk. And we also envision robots to collaborate with us at the workplace. What all these examples have in common is that there are large prior uncertainties that are very difficult to predict ahead of time. On the road, that could mean the weather conditions, or in the sky, that can mean the different wind conditions. In collaborative tasks with humans, that may mean different preferences and characteristics of different people. But nevertheless, the robot has to actively make decisions, and we expect safe and high performance behavior. And so typically how such a problem of decision making was solved by the controls community is in the following way. We would establish a system model, so that's usually a differential equation that describes the motion of the robot in the given environment. Then we would do some system identification, which may involve some data collection. And so that system identification could identify certain inertia parameters of the robot. And once we have this full model, then we would design a controller that makes decisions at every moment in time. This works really well in controlled environments, such as these robots on the assembly line. We can also study how robust this approach is towards model errors, or errors in the environment that we didn't consider, and when it works and when it doesn't, up to which point it works and when it doesn't. And we can incorporate safety constraints in formulations such as model predictive control. So we can explicitly say the robot needs to stay on the road, and we want to apply actions to the robot that guarantee that the robot stays on the road. And these guarantees are satisfied under the assumption that our model is correct. So the advantages of this approach is, we have models that really describe the behavior. We can use these models for feedback. We can guarantee safety. And we can study the worst case scenario. So up to which point does our controller work? Up to which point of model error? But what it doesn't consider is that the worst case behavior is not always the best. So if I have a robot that should drive, for example, on the road, and I have various road conditions, right? The best thing that a standard control approach could do is trying to model this, trying to model the full range of possible road conditions, and then designing one controller that guarantees safe behavior for the robot. There are, of course, so overall learning and incorporating data is not really considered. Everything is relying on a priori knowledge. So a priori, if I would kind of specify the different road conditions that a robot could experience, and then based on that, I would try to find a controller that makes safe decisions despite, a variety of road conditions I could experience. There are, of course, adaptive controllers in the controls community, but generally, the controls community is not good at leveraging historic data and learning, possibly even offline, from historic data and improving the system. So the performance here is usually limited by the system understanding. So typically this means either I have model errors, or I'm very conservative because I assume, I can experience a large range of different conditions, for example, different road conditions. And then to find a controller that works for all of them, the controller is quite conservative. So I would basically thrive on a summer day, like I would thrive in winter, just because that's the safest I can do overall. Then there's the field of reinforcement learning and machine learning. And typically, I just try to broadly categorize, right? So don't be offended if you do reinforcement learning with models. Typically, reinforcement learning would not use a system model, completely rely on data samples, and then optimize the controller through exploring actions in the real world. So it looks like this. So I have a learner or controller. It applies actions to the robot. It observes the state and also the reward, which is related to the performance on a given task. And then it optimizes the actions over time. So it learns control actions based on the state. So what is good about this? It learns relevant data for a specific task, which is defined through the reward. The performance is typically in expectation. So it does not compare to the robust control approach explained, where it tries to find a controller for any possible, that works for any possible condition, for example, any possible road condition. Usually performance is here defined in terms of expectation, at least in the more traditional works. So that these, reinforcement learning has made amazing progress and has surprised us all with performances on games like Go, or in simulation environments with complicated virtual characters, and also in kind of very specific lab settings, where here the robot tries to insert a piece into this wooden box. But it has mostly been demonstrated in controlled environments and relatively environments where safety does not play a major role. So the advantage of this approach is it collects data, learns directly from data, doesn't require a model. It can trade off exploration versus exploitation and optimizes for the average case. But the disadvantage is it is usually not safe, and safety is not incorporated in these approaches, because in the exploration phase, you try different actions and just observe the behavior, and these actions may possibly be unsafe. And it's also not particularly data efficient. That's why a lot of the examples are in simulation or simple robot cases. So it does not guarantee safety and doesn't make any kind of guarantees for the worst case. So here the safety is kind of limited by the lack of the overall understanding of how reinforcement learning works. So the idea is, can we combine the two things? Can we combine models and data to achieve systems that learn and adapt, but at the same time are safe and data efficient? To aim for these applications in the pictures, right, where robots directly interact with people, where we don't want to show a robot 10,000 times what to do in our kitchen till it knows it. So data efficiency is important, and safety. And so what we've done in our research is to achieve performance and safety for robotics applications with prior uncertainties by combining machine learning, which is really the science of data and inference, with control theory, where, you know, control theory for a long time has studied feedback and automation, and has come up with concepts that describe the performance of these kind of closed loop systems that make decisions, and then the decision affects the next state, and then that state affects the next decision. And so we have worked in my lab with lots of real robots, and that also motivates some of the approaches that we have been developing. And so here you just see a range of robots. So it goes from different flying platforms to self-driving vehicles, and more recently, these kind of mobile manipulation platforms that could be used in home environments, but also warehouses. And so a particular focus of our research was on online learning. So how can we learn, can the robot improve as it moves in the environment? And yeah, real robot experiments. And so when you come to our lab, you actually see robots moving all the time, even now, despite the pandemic. So this video just summarizes, gives you a quick glimpse into the type of robots we work with and how they look. So this is a swarm of robots, and here we need obviously accurate motion. We use this kind of swarms for monitoring in indoor environments. We also fly outdoors based on vision, where we have winds up to 55 kilometers per, or we fly up to 50 kilometers per hour, and have winds up to 28 kilometers per hour. This is an off-road vehicle that we have been using for some of our research. And for the last 3 years, we have been participating in a self-driving car competition sponsored by General Motors, where things have to work with, you know, at competition time and day. And here you see the mobile manipulator. So hopefully this gives you an idea where we are coming from, and which type of systems we want to work with and improve over time. And this I like to briefly show. This is kind of the bigger picture that how I map our research, but also, I guess, generally the progress in robotics. On the one hand, on this vertical axis, you know, we aim to build robots that can do more and more complex tasks. You know, the industrial robots can do single tasks, single very predefined tasks, but eventually we want to go to interactive human-centered tasks. So again, the task complexity plays a role, but also the complexity of the system and the operating conditions here on the x-axis, right? If the environment is, a system is less complex if we have sufficient prior information to control it, so we don't even need learning. And if the environment is partially unknown and changing, that makes it more and more complicated. And so I can put some examples here, from industrial robots to self-driving to your, you know, home robot. And so the first part, when we have sufficient prior information, we can use model-based planning and control, and we don't need any learning because we have all the prior models that we need to do this task. And just because I assume that there are multiple people here that have more machine learning background, I want to kind of give you the quick summary of control theory. So feedback control is something that was studied since the 1870s. So since the first machines, you know, were developed. And the idea is really that you have a robot, you measure certain quantities, and you feed them back into the controller. The controller has also access to the desired reference signal, and this controller computes this input to the, in this case, to the system or to the robot. And ideally, the output follows your desired reference signal. So that's kind of a baseline control loop, and the controller is usually designed based on knowledge about the system. And so this kind of control theory focuses on dynamic systems and continuous states and actions. It assumes an accurate class of models, and then it can kind of give you closed loop performance guarantees, right? And that's, I think, something that can be very interesting for machine learning researchers as you continue using your machine learning techniques in robotic systems. They're kind of in a closed loop. And so, control theory has, always studied stability. So if I have a bounded input, can I always guarantee a bounded output? So for a flying vehicle, this means, will I stay in the air and not crash, despite maybe some, perception errors, some controller errors? Can I be stable? They have also looked at the performance of this closed loop control system, like, for example, how close is my output tracking my reference signal? And they can derive, formula results for this. And in control theory, robustness is a big topic. So robustness generally means stability, and performance in the presence of bounded modeling errors. And so it basically gives you worst case guarantees. I bound my errors in my model, or generally my errors in the closed loop system. And I say, if I have these bounded errors, my system still performs at a reasonable level of performance, and it doesn't become unstable. So the car doesn't drive off the road, the flying vehicle doesn't crash. And then finally, they can also give formal guarantees for constraint satisfaction under the assumption that a model class is known, and under this assumption, for example, that these errors that we have in the closed loop are bounded. So what I want to say with this slide is, in control theory, the closed loop properties and characteristics have been studied, but under very simplifying assumptions usually. The biggest simplifying assumption is that we have accurate models and accurate bounds for the errors. But then, they could study and guarantee things like constraint satisfaction, robustness, and certain levels of performance. And so I think these techniques are still interesting because, control theory has always looked at this closed loop, but in a very, very simplified fashion. But now, today's kind of closed loop systems look much more complicated. The robot has multiple machine learning algorithms running for perception, and then those are, fed into a big estimator, and then this estimator, which can also be complex, very complex, outputs the state of the robot, and then there's multiple levels of motion planning and control. So for self-driving car, there are many, many components and many, many more uncertainties. And these theories would not directly apply, but maybe could inspire some new developments. So how do we go from kind of this, the traditional control theory can be used, to these more interesting application areas where my story or my promise really, we need machine learning because we have limited or we don't have all the information ahead of time. And so in the talk, I want to kind of show you some of the things we have been doing to combine control theory and machine learning, and show you in particular how we started with a single robot learning a single task. We allowed it a training phase, and we have just some unknown but static conditions, to how we extended this to a multi-robot framework, learning multiple tasks. The robots continuously improve as they operate in the real world, and they can deal with changing conditions. And so let's see. The first step was, okay, a single task and we allow a training phase. And the example you can envision is flying a slalom with a drone. So that was kind of the application scenario that really motivated me to get into learning in the first place. So we wanted to really race the slalom with a flying vehicle. And so this was a single task, and we allowed it to learn through practice. So similarly, if you would, I don't know, you would change your career and suddenly would race, do car racing, right? You would practice a lot on a different course to optimize your strategy. And so what we did here is we have this baseline underlying control system, but this wouldn't work well. So what we really saw, and that really motivated my first work in machine learning, is that we wanted to fly this along this blue line, but really what the vehicle did again and again and again is it flew off the path along these colored lines. But these colored lines were all on top of each other. So whenever the robot did something, it did it consistently wrong, right? So that was kind of saying, okay, it's a repetitive error or something. You should be able to compensate for this. And this was really triggered by model errors in our system. And so what we did is we tried to understand the model error by looking basically at these trajectories. How my reference signal, which was the blue line, maps to my output, which are these colored lines. And then we use that to compensate the reference signal, to change the reference signal such that the mapping from my input to my output is actually, a unity map. So my desired output that I have here on the left and my actual output are the same. And for that, we use basically a policy gradient method. So we iteratively changed the reference signal in a way that gets us closer to the output that we really want to see. And so you don't have to see all the details, but basically we said we take the old reference signal from the previous iteration, and then we look at the tracking error that we had, and then we use an inverse model, which basically, and that was just our approximate model. This was not learned. So this tells us if I'm a bit too far to the left of the trajectory, how do I have to change my reference signal to get it a bit closer to the reference trajectory? And this just has to be correct to first order, such that I understand how a change in the input makes a change in the output. And then we could actually, since we had this underlying controller, we could guarantee that our vehicles always stays in the air as long as our reference signal stays bounded. And so the interesting part here is we could really learn very quickly because our model of the system was at least accurate to first order, and we could use it here in the gradient update step. And then the architecture helped us as well, right? Because since we are control engineers, we knew how to stabilize the vehicle and keep it in the air, and we only changed the reference signal. And that makes, by closing this underlying loop, you saw that it made the errors very repetitive, and having repetitive errors is much easier to learn. And so here you see this. So if we made the underlying system less repetitive, which means we learn the desired turn rates, then we also learned, but then once we converged to an optimal input, but the output was still very, had a lot of variation. All the red lines are basically from this same input, but the output changed so much because our underlying controller didn't make the system very repetitive. But if we used what I showed you before, and we kind of learn the desired positions, then once we have learned the input, the behavior is very repetitive. So the architecture really makes, I think, a big difference, and often is not prioritized in, or not, we usually don't talk about this so much, that there are always some underlying controllers that make a system repetitive, right? If you work with robot arms, you learn at a certain level, but there are many underlying control loops that control each single motor. Yeah, but this architecture allowed us, we practice above the poles because we couldn't guarantee that we don't fly into the poles during the learning. But once we saw we can make it, and which usually took this 3, 4, 5 iterations, we can actually demonstrate the behavior. And here you see the learned result for a different configuration, which we learned from scratch. And here's another task, a triple flip. So a quadrotor should do 3 times 3, 360 degrees of rotation, which is very challenging, and the dynamics is difficult to model. And it learns to start, to end up where it started. So the goal is, yeah, you start here, do a triple flip, and then end up where you started, and it can learn that. If you see here, it goes far away, but then at some point it gets closer to stopping where it started. So this was learning a single task through practicing the single task. So we allow a training phase. Now, how can we extend this to multiple tasks? So in the previous example, a new slalom configuration, we would need to relearn again. In order to extend this, we use the same architecture for flying vehicles, but instead we now assume this big gray box is a dynamic model, and we need to invert this. So we learn an inverse model block. Basically, the green block should cancel the gray block out. And we use a deep neural network for this, but you could probably use different things. And so what our control theory tells us, like different nonlinear regression techniques, what our controls in, I guess, knowledge tells us is that if I would perfectly know the dynamic behavior of this gray box, which I don't, then the green box would depend on 2 input features only, the state at the current time and the desired position r steps in the future. And r is basically representing the delay in the gray system. And so what this tells us is I don't need to somehow do a neural network that takes the current state and a whole sequence or history or the full trajectory, y desired trajectory. We really need only the value r steps in the future. And we also showed that just using that value compared to more of a window of the desired output trajectory doesn't make a difference. So we can just use this one single value, and that makes our learning much faster, and we need much less data. So we still leverage our control knowledge. And because of the architecture, we can again guarantee that at least the vehicle stays in the air. And so, yeah, we can test this now on many hand-drawn trajectories. And we purely train on periodic sinusoidal trajectories, and then we test it on these kind of very, I guess, random hand-drawn trajectories, and we see a 62% error reduction. And yeah, a key part that allowed us to be data efficient was understanding, I guess, overall this gray box, and therefore carefully choosing the input features for the neural network, which made it much more data efficient. And so here you just see a video, which is kind of nice. So if you could come to the lab, you could draw on this tablet, and then you could see the vehicle fly. And so if you had drawn the red line, and a traditional controller was doing the green line, which was not great. And so now you see with the neural network, we stay much closer to the red line. And so we did a lot of tests for this. And this was just recently online published with lots of experimental data in IJRR. So if you want to see a lot of the more detailed results. But yeah, people drew, and then you could see that with the neural network, it tracks the drawn red line pretty closely. So that was kind of one step towards multitask. Instead of learning just a reference input, we learn a model, an inverse model to be accurate. Now, our kind of solution towards getting rid of this training phase, we even had a training phase for the neural network part, right? There we basically trained the network on lots of periodic motion. So we had 20 minutes of flying circles and spirals, and we used that data to learn. So now, how can we avoid this training phase?
Quick question.
Yeah,
Angela?
go ahead.
Sure. So in learning all of these, do you require the ground truth to be perfect, like from a motion capture system?
Yeah, so yes, for everything I showed you so far, we use a motion capture system. I think it's not a requirement, but I have no hard data to show you how the performance would be. My expectation is just you can only get as good as your measurement or ground truth, right? So if I have noisy ground truths or biased ground truths, I can only get accurate up to the level of my ground truth, but it should still work. Yeah.
Thanks.
Yeah, so going from a training phase to continuous improvements, we look at probabilistic formulations. And so the architecture now looks slightly different. So we now model the disturbance as a stochastic process and then use robust control. So basically find a controller for our worst case. Or for all possible models. Find a controller that works for all possible models. And so here's a video that motivates this. So we drive this robot, and we are not accounting for model uncertainty or constraints in this case. We just tell the robot, follow this path, and carefully select this path to show the problems with model-based approaches, but here you collide with these pylons. So how do we do this? So the disturbance model that we use is, we assume it is additive. So we say we have an a priori understanding how, for example, this ground robot moves, but then there's something we don't model. The detailed dynamics, the interaction of the wheels with the ground, many things that influence the behavior, and we just say it's additive. That's a choice, and just the easiest to do. And then we basically say this is something we don't know ahead of time, this G, and we model it with a Gaussian process model. And so you can, if you look here at the bottom right, it could look like this. This function we don't know. And initially, we just say this function lies anywhere in this blue shaded region. And we want to find kind of a controller that works no matter what G is, as long as it lies in this blue shaded region. So we make this assumption that the function lies with high probability in this blue shaded region. So that's a prior assumption. But then we collect data as we drive, and learn more about the function. And if we get 2 data points, we already have narrowed down where this function could lie. So it could lie, any of these thin blue lines could be a possible representation of G. Yeah, And what is also important is why can we shrink this envelope even between two data points, so even here between the two data points, because we made some continuity assumptions. That's also important. We assume that G is at least has a maximum rate of change. So there are some assumptions, but this way we collect more and more data. The uncertainty shrinks. We get a better understanding of how the system works, and we get a more optimal controller for the current situation. So, you know, the smaller this blue shaded area is, the more optimal I am for the given situation. Usually robustness means being conservative, because you do something that kind of works okay for a large range of different models. And so for our specific driving example, if you look here, well, how did this work? So we use, for robust control, we use a model predictive controller. And model predictive controller, I think, is really powerful. So if you have never heard of it, I don't repeat it here or explain it in detail, but it's basically at the given moment, I look into the future and say, if I now apply a sequence of inputs for the next 10 seconds, based on my model, where could I end up? And since we have a stochastic disturbance model, I could end up anywhere in this red shaded area, because I cannot perfectly predict where I am, because I only have, a probabilistic model. And so then model predictive control optimizes the input sequence to the robot over the next 10 seconds. And in our case, since we use this stochastic model, what it would do initially is, and because we also incorporate state constraints, we want the robot to stay on the path with high probability. What it does initially is it slows down. So you see over the 10 seconds, it only gets up to here, but the uncertainty envelope stays within our path bounds. And then as we go on and we learn more about our model, our uncertainty in the model reduces, and then we can try faster while still guaranteeing with high probability to stay on the path. So basically, in this case, a more knowledge about the model means higher speed. And yeah, optimal control optimizes over a prediction horizon, then applies the first input of the optimized input sequence, and then re-optimizes in every time step. And so, yeah, the nice thing about combining it with robust control is that we can give some probabilistic worst case guarantees in terms of satisfying state constraints, such as staying on the path. And so here you see an example. So we drive the same path as I showed you before. And this is the first trial, and we made the initial uncertainty high to be safe, and therefore we drive pretty slowly. But then as we gather more data, our knowledge about the system becomes more clear, and we can drive faster. And here you see actually trial 1 and 3 on an off-road path that goes along fences and trees. And on the left, you see the time we drive it, and on the right, the third time. And you see, especially on straight sections of the path, we go quite fast, 3 meters per second, and definitely much faster than during the first trial. And then we finish this section of the path faster than in the first trial. So yeah, we have done actually a number of recent works in this direction of using the probabilistic formulation and doing continuous improvement. If you're interested, I'm happy to touch base later on and discuss this further. For example, we have combined it with differential flatness, Gaussian processes with differential flat systems, which also seems promising. And finally, how can we get from a single robot and static conditions to a multi-robot, so multi-robot transfer learning and changing conditions? And for that, our answer so far is the same for both things. We need somehow a combination of fast adaptation and long-term learning. And I think this is just first approach. We're still working on this. Have some ongoing work, but now compared to the previous example I just showed you, is we assume somehow this can change, this function. It can change with time, or it can change because we change the robot. And so the architecture that we use is we have a very fast adaptation that tries to compensate for these changes over time. And then we have an outer inverse map that looks very similar to the results I showed you with the hand-drawn trajectories. So what this adaptive control does, it makes this gray box, or this baseline box, the dashed line box, try to behave like a reference model. So it tries to guarantee us, and there are actually formal guarantees under some assumptions, of course. It can give you some formal guarantees how closely this dashed box follows a certain reference behavior. And then we do inverse model learning, similar to the hand-drawn trajectories. And so if you do this, yeah, the nice thing is that L1 adaptive control under assumptions can give you some guarantees. And again, I think that's really interesting to study because, yeah, they give you guarantees on closed loop systems. So I just want to show you one work that we did, where we have one robot that learns one trajectory, and then we try doing a different trajectory. And so these are the different trajectories, and the results I show you is I use one source trajectory from the source robot and then test it on the target robot on 6 different trajectories. And I see how well my knowledge from the source robot can be used to do these different 6 trajectories. And then I do this for all combinations, and that's the results I show you. So what do you see here? So the red dot with white in the middle, that's basically if I do this task without any learning on the target robot, the tracking error that I get. Then the solid red dot is if I learn that particular task on the target robot alone. So I allow the target robot some training phase and I allow it to learn. It's kind of the best that we can get. I would say that's kind of the best it could possibly get. And then this box plot shows the transfer results that I can get from transferring from the source. And it's kind of from the different 6 trajectories. So it's kind of the summary. So no matter, basically what it says is no matter from which trajectory I transfer, I do pretty well. I get very close to the ideal solid red lines without training at all on this new robot. Right. So we can get 74% error reduction with transfer loading. And the target robot doesn't have to learn at all on its own. So you could use that if the target robot is very expensive to operate. You could train on some similar other robot. The question of, maybe that's something I can say here already. The question, how similar have these robots to be for this to work? This is an open question, and we have started to explore this. That's even an open question for core adaptive control. So how similar do these robots have to be for this to work? It's ultimately a question about this underlying adaptive controller, and it's not answered. There's no clear answers to this. We have started to look at basically to characterize the similarity of 2 systems, to understand better how transfer learning works. And I think we look at this more broadly now as well, because this is even interesting for sim to real, right? Applications, which there are many and lots of reasons to do training and simulation and then go to the real world. Like, how can we specify the similarity between simulation and reality, and when can we guarantee that transferring from simulation to the real robot is actually of advantage, right? It could also make it worse if the simulation is way off from what the real world is like. So yeah, so we use and explored how we can use kind of a more hierarchical structure with underlying fast adaptation and long-term learning. And so finally, we have also some possibly interesting results for some of you. Happy to chat further if any of this is relevant. So we have some more formal results on safe reinforcement learning, model-based reinforcement learning, safe model-free learning, some active learning results, and as I mentioned, this characterization of system similarity for transfer learning. Yeah, I think that's, don't go into these details. And finally, over the past, I have always done work of flying multiple vehicles, and we have done some distributed learning work. If anyone is interested more in multi-agent learning, we have a test bed with multiple flying vehicles where you could possibly test these things, and which motivates our work. So going back to the big picture, our work has kind of fallen in these categories. You can partially categorize them, try to fill the gap, but you see all the gray boxes. There are no publications from my group or possibly from some others. But really, I think it's really important to think both about the complexity of the system and the task to eventually go to the top right corner, which would enable a more seamless interaction between robotic systems and the physical world. So what is next? Some more recent work is mostly on dynamic environments, more complex missions and collective learning, and more human-robot collaborative tasks. And I want to just show you two brief videos, what we have done more recently. We started working more with this mobile manipulator. And so here you see a bit of interaction where the student Adam, in this case, pulls the robot on its own avoids these obstacles by following him. Or here we started kind of really exploring the dynamic capabilities of this robot by catching balls. And the video for our IROS paper shows more variety of throwing, where we really have to be very accurate in our motion in terms of both the accuracy in the space, but also in terms of the time. And and here we also use some learning, the inverse learning component to make this catching work. So to conclude, I think there's really a broad field in robotics to guarantee performance and safety for applications with prior uncertainty. And I think all roboticists here on the call aim for kind of expanding the operation envelope of robots and enable them to deal with more complex and changing environments. And so I guess the one take-home message is, think in order to enable these new applications, these systems must learn and adapt offline or online or both. But we also need safety and data efficiency if we talk about robotics. And so a lot of what I've been doing with my team is combining machine learning with control theory, and mostly control theory is used to understand and characterize and prove things about the closed loop behavior of the full system, including the learning component. Yeah. So finally, this is of course due to really great students who work with me and some of my main collaborators. And yeah, if you go to our webpage, you also find the contact details of all of the students. if you have particular questions about particular publications. And then, yeah, if anyone looks for opportunities after graduation or to do the next step in your academic career, consider joining us. We have lots of also collaborative activities with Montreal. We have the Vector Institute and Mila in Montreal. And then my team is part of the ENSA Canadian Robotics Network, which is actually led by a professor at McGill. And it's kind of a cross-Canadian robotics network. So there's lots of, I think, really exciting initiatives happening in Canada in general and between Toronto and Montreal. So yeah, if you're interested in the research we are doing, happy to chat about opportunities. Thank you.
I have a bunch of questions, but I think maybe we can field questions from the panel, or I'll dive in.
Sure, go ahead. Like, I'm assuming someone will push in the chat if they have a question, and we can get to them.
So that really great talk, Angela. Thanks so much. I actually wanted to ask a little bit more about the thing that you mentioned about characterizing the similarity between systems. How are you thinking about that problem? Because like, do you think about it in terms of input output? Like,
yeah, I have to say our approach so far is very, still looks at very simplified systems. Like, for example, we started with just with linear systems and looked at, how is similarity characterized between two linear input behavior that's linear, and we look at the input output. This is a much broader question once you think about 3D rendering of the environment, right? So there's lots, I guess overall what I've done is usually always more on the decision-making and control side, but there's for everything the perception side that makes this all much more complicated. And yeah, and we did some work also incorporating, thinking about, I guess, incorporating the perception and still trying to characterize the closed loop behavior. That's ongoing. We have some simple examples. So for example, if you do vision-based flight, right, the perception makes, the quality of the perception may be different areas. And depending on the quality of the perception, I may need to adapt my controller. If I'm not certain about my perception, I need to be probably flying more carefully. So these things we have started looking at. But yeah, similarity, we started super basic. Yeah, just.
So because it seems like on some, like, what are you're gonna like have a number that's gonna like describe similarity or something. But in thinking about the problem statement that you've got, like what you really care about is like, are these things similar enough so that they're within the bounds of whatever the like robust controller that I have or whatever. And so I've been thinking about some similar things lately, and I don't know, it seems like it's hard to decouple. It's hard to make a meaningful metric of similarity without the considering of the specific task that you're actually trying to do in some sense, right? Like, what do you think?
Yeah, I agree with you 100%. So one characterization that we use for similarity is, can I do a given the transfer of data, can I do the task now better than without the data, right?
Right.
So that's one characterization we use. And yeah, that's task-based. Yeah, in very simple cases, you can make this task independent if the system is linear. Then you could just say, can I do any task better with the data than without. But
Right.
it's yeah. I think this probably only works for linear system. I have to think about this more. But yeah, for
I have a somewhat related question, but in a different dimension. Like throughout your talk, you described how we identify models of robots. Like, yeah, the most recent question being, can you actually tell two robots apart? But in most of these cases, a robot model seems to be static over time. Am I right in assuming that? Like in real robots, you'd have things like wear and tear. The robot's dynamics just change over repeated use. What are your thoughts about tackling some of these issues?
Yeah, I think honestly, like the environment and the robot are kind of static, meaning the behavior doesn't change over time. It's almost everywhere in learning and in more learning-based control, and also in reinforcement learning, like, for the most part. I think the last part that I showed you with this underlying adaptation, right? That is one option, I think, where you have this quick underlying adaptation that kind of compensates for these ongoing changes and makes the system behave on a higher level always the same. So that's one way to do this. One of my students has also done something else where you try to characterize from the data, am I still following, like, is my model still accurate, right? I have a probabilistic model, and then I can check the data points of the last 10 seconds. Can they be explained by my probabilistic model? Or would my probabilistic model say these data points are very, very unlikely? And then if you have that, then you could say, okay, now I need to start from scratch and behave very conservatively first, and then learn again. So yeah, but
I completely agree. Like that's an even bigger challenge, like trying to detect when your model is gone. It's no longer valid.
Yeah, and these changes, I guess changes are important because it's not only the robot that can change, but also the environment, right? And I guess in almost every kind of subdiscipline of robotics, you assume static environments and or robot models. Also for planning, I mean, for many parts of the planning, yeah.
Question from the chat. How to balance between safety and exploration efficiency?
Yes. Yeah, I guess overall, not all of our approaches explicitly do the exploration well. There's one in Europe's work on safe model-based reinforcement learning. There we have this explicit trade-off between exploration and exploitation. But what can I say about this? I guess you, in some way, okay, if I want to be in some way, you could be more data efficient when you have the safety constraints, because if you do this properly, then you would not test actions that lead to unsafe behavior, right? And so testing these actions does not make sense. It's not very data efficient generally, because you never want to do those. Does that make sense? Like, why should you test or explore unsafe actions? But yeah, I wouldn't say that there's yet good algorithms that, I guess, constrain exploration with safety bounds and are very efficient. Yeah, I guess the one work I can point you to is we did automatic controller tuning using safe Bayesian optimization. And there we basically do this. There is a clear trade-off between exploration, exploitation defined through the Bayesian optimization framework, and we only explore actions that are safe with high probability, and therefore we constrain our search space. Yeah.
I had another question. So with respect to perception, so you mentioned something about perception, and I understand that, you know, I buy that you could do a lot of the like inference over state from vision, and it would, you know, be mostly the same. But in some of the like applications that you cite, there's also the perception of the external world to the robot, like when the quad rotor is slaloming through the pylons, or in the like most complicated situation in autonomous driving. And like generating safety guarantees in like autonomous driving is like what everybody wants, but all of the approaches that I've seen based on these kind of formal method approaches, they just don't scale. There's really, I don't see a path forward for those kind of like formal methods to scale, but I could be wrong. But so how do you view like all of this in the context of like the uncertain world that you could be operating in?
Yeah, I guess a first thing to say is, right, you can always only make any proofs or give any guarantees if you make some assumptions, right? So you need to make some assumptions about the uncertain world, at least like, you know, the set of possibilities that you could encounter. And so then, yeah, and so that is already a limitation in itself. But I think still not impossible to do, because you could be very generic, right? In self-driving, oh, this is some LiDAR cloud that's close to me. I don't know yet. I cannot kind of characterize, do whatever, an object label, but it's something. And if I have this, how can I be safe? Right. But I agree there's a big gap. And that's not the first time, I guess, in history in controls and overall. It has often, methods have been broadly used in industry and had no proofs yet. So it's not the first time. But I guess at least you want to have some safe. I guess you should still have. And I'm not a safety for autonomous driving expert. I know all the current work in all the detail, especially not the formal methods work so much. But you should still have a safe backup. And I think for driving, that's easier than for flying vehicles, because you should always be able to somehow stop. Right? So maybe at least you can have, for the worst cases, some safety mechanism. I think that may be possible. But yeah, you have to take into account that every component of this very complex system could fail, right? Yeah. And how that failure manifests itself is difficult to understand. And so, yeah, it's tricky. And usually the worst case things happen, or the worst things happen if multiple things fail, which is very unlikely, but could happen. Yeah. Yeah, I don't have a good answer, really good answer.
Okay, I had another question then. So on the
Really?
like,
Hey, Liam.
yeah, go for it.
I have to go soon, so I wanted to ask this one quick one and say hi to Angela.
Hi, James.
Just one quick question. So in the very early work you were talking about, where you're using a neural net to learn effectively a modified reference signal, like that makes a lot of sense. But I guess my question would be, like you in sometimes you have a prior, like, and your prior is the inverse dynamics of the actual model. And so what I've been really like my big pet peeve is F equals MA is really good and we shouldn't throw it out. And so I'm just wondering, and it's pretty obvious what I'm going to suggest, which is, well, why don't we use our F equals MA model as the prior and then just learn the delta?
Yeah, that's a good question.
So okay, so my first question is do you do that? And my second question is, why don't people do that? Like, I think it's pretty obvious. but I gather it's not super. I've only heard of one person doing this, and I don't know why it's not done more. I wonder if you have any comment on that.
I think we use the prior model quite a lot in our work in different ways, right? For example, for the slalom learning, we actually use it to compute this or to get this gradient, how to modify, how to get from a tracking error to the next reference input. For our work on the Gaussian process, we basically say our Gaussian process is an additive component, kind of modeling the model error. So there we do it. And I think it's also, to just get a robot moving, you need something, right? You cannot kind of have nothing. So for the particular question that you had, there I think we could still do it. So there basically, yeah, we learn just the neural network, and we have not done the check what is if we just use the delta. What we have, however, done is we checked, and I think this is also part of the IJRR paper, we used traditional methods of inverse model learning, inverse model identification, or our actual, yeah, we identify the model with traditional method and then invert it. And so, and that is worse. So there is this delta, but how to, I think, yeah, we could have done this. Just basically learning the delta to the inverse. I think it just was, since we do anyway offline learning and we get the input output data, we could just learn this nonlinear math. Yeah, it may have, yeah, you could probably improve data efficiency and probably get away with something simpler than a neural network, maybe just a linear thing. Maybe, yeah, maybe not.
Yeah.
I guess. Yeah. There we didn't do it. Yeah, agree.
Yeah, and just one other comment for kind of more the general audience, which is I really love that you emphasize you're not actually touching the control loop. Like I think a key aspect here is that if you want to do learning in the loop, that's like infinitely harder and more dangerous.
Yep.
And so you really, what I love about this is you bootstrap what we're good at. We're good at starting with a very simple model, wrapping a PID loop around it, and that got you flying. And then you go away and you learn the rest. Like I think that's a really great approach. So I just wanted to basically emphasize that I think that's awesome.
Yeah, I definitely, I am on the same page. Thanks. Yeah, I do think this is, this is also sometimes not clear for machine learning or reinforcement learning approaches, because often they do some closing of the loop and they do this and they don't mention why and how and what was the reason to do it in a certain way. And I think usually it is because you make the system more repetitive and I guess, yeah, flying in the first place, and then you learn. Yeah. I think that's definitely an interesting area. Yeah,
thanks so much.
Thanks.
All right. Yeah, since we're already like 10 minutes over time, I really don't want to take any more of your time, Angela. Thanks so much for talk, and yeah, let's all thank the speaker again.
Oh, I mean, thank you so much for the invitation, and I hope we stay in touch, and everyone on the call. It would be great to kind of learn more about